You ever stop and think about what's really powering our cars? Or what that plastic bottle in your hand is made of? It turns out the answer to these questions, and so many more, comes down to a really simple family of molecules. We're talking about hydrocarbons. Let's dive in and see how these basic building blocks pretty much shape our entire world.
Yup, you got it. They all come from hydrocarbons. I mean, these things are everywhere. They're molecules made of just two things, carbon and hydrogen. And while that sounds almost too simple, they are, without a doubt, the quiet architects of modern life. If you really want to get a grip on chemistry, you got to start right here. All right, so here's how we're going to break it all down. First up, we'll get a proper introduction to the hydrocarbon family and its main branches. Then we'll spend some time with the calm, stable members of the family, the alkanes. After that, we'll meet their much more reactive, kind of exciting cousins, the alkenes and alkynes. And we'll wrap it all up by peeking inside the chemist's toolkit to see how these molecules are put to work. Okay, let's get down to the absolute basics. You can think of almost any complex organic molecule, seriously, from life-saving medicines to the clothes on your back, and trace its origins right back to this one essential family of compounds. They are the true foundation. The definition itself is just beautiful in its simplicity, right? If a molecule is made of only carbon and hydrogen atoms, it's a hydrocarbon. That's it. But, and this is a big but, don't let that simplicity fool you for a second. From this one basic recipe, you get an absolutely mind-boggling variety of molecules, all with completely different properties. So the hydrocarbon family really splits into two main branches, and it all boils down to how those carbon atoms are holding hands. First, you've got the saturated guys, the alkanes. They only have single bonds, meaning they are completely full, just jam-packed with as many hydrogen atoms as they can possibly hold. Then, on the other side, you have the unsaturated crew, the alkenes and alkynes. Because they have double or even triple bonds, they've got room to spare, little openings where they can form new bonds with other atoms. Let's start with the bedrock, the literal foundation of the hydrocarbon family, the alkanes. These are the simplest, most stable of the whole bunch. They provide the sturdy structural backbone that pretty much all other organic molecules are built on. And that stability, that's exactly why they make such great, predictable fuels like the methane in natural gas or the propane in your grill.
Alkanes, which you'll sometimes hear called paraffins, a cool name that actually means little affinity for reacting, are all about their single bonds, which we call sigma bonds. This structure, which follows that neat little formula CnH2n+2, gives each carbon atom this 3D tetrahedral shape. But here's the most important part. It allows the molecule to spin freely around those bonds. Just picture beads on a string. They can twist and turn all they want without ever breaking the string. Now, because of that free rotation, the molecule can twist itself into different 3D shapes, or what we call conformations. Sometimes it ends up in an eclipsed form, where the hydrogen atoms are all lined up, kind of bumping into each other and getting in each other's way. But it prefers the staggered form, where they're spread out with plenty of room. That's a lower energy, much more stable state. See? Even atoms appreciate having a little personal space. Alkanes are so stable, so unreactive, that you really have to give them a good kick to get them to do anything, usually with something like UV light. This kicks off a chain reaction called free radical substitution. You can think of it in three parts. First is initiation, where light creates a superreactive particle. Then comes propagation, where that particle starts a chain reaction that just keeps going and going. And finally, termination. That's when two of those reactive particles find each other, pair up, and the whole thing comes to a stop. Okay, now let's get to the more adventurous side of the family, the alkenes and alkynes. With their double and triple bonds, these molecules are way more reactive, just itching to get involved in chemical reactions. This right here is where the real fun of building molecules begins. So what's their secret? What makes them so reactive? It is all about something called the pi bond. You see, that first single sigma bond is super strong and stable, but the extra pi bond, it's weaker, and it's much more exposed. It creates this cloud of electrons sitting above and below the molecule, which basically acts like a big, tempting handle that other molecules can just fly in and grab onto. This reactivity leads to what we call addition reactions, where that grabbable pi bond breaks open to form new single bonds. But that brings up a really good question.
If you're adding a molecule that has two different ends, like hydrogen bromide, how does the alkene decide which piece goes to which carbon? Well, the answer comes from a super simple but really powerful guideline called Markovnikov's rule. And the easiest way to remember it is this: the rich get richer. It just means the carbon atom that already has more hydrogen atoms attached to it gets to add the new one. It's an incredibly reliable rule of thumb, kind of like a chemist's best friend for predicting how these reactions are going to turn out. Alkynes, though, they have another really cool trick up their sleeve. When that triple bond is right at the end of a carbon chain, the hydrogen stuck to it is actually surprisingly easy to pull off. When that happens, you're left with a negatively charged carbon atom, which is basically like giving a chemist a piece of molecular superglue for building bigger and way more complex structures. It's a huge deal. So you see, all these differences in reactivity, stable alkanes, reactive alkanes, they aren't just random facts to memorize. They form the very heart of a chemist's toolkit. By understanding these different family personalities, chemists can pick exactly the right molecule for the job and build totally new things with incredible precision. And this is where the pure artistry of chemistry just shines. Get this, a chemist can start with the exact same alkyne, but just by choosing a different chemical to react it with, they can create two totally different products. One method gives you a cis-alkene, where the new hydrogens add to the same side. Another method gives you a trans-alkene, where they add to opposite sides. It's like being a molecular architect, deciding with absolute precision how every single piece is going to fit together. It's amazing. Another really crucial tool in that toolkit is a reaction called ozonolysis. This one uses ozone to make a super precise cut right through a double bond, basically slicing a molecule in two. You can think of it as a pair of molecular scissors. It lets chemists take big molecules apart into smaller, more manageable pieces, either to figure out what the original looked like or to use those new pieces to build something else.
So let's bring it all home with our family analogy one last time. The alkanes, they're the reliable, super stable members of the family. The alkenes, with their reactive double bonds, are the social butterflies, always looking to make new connections through addition reactions. And the alkynes? Well, they're the most reactive of all, with a unique set of skills that make them unbelievably versatile players in the world of chemistry.
When you boil it all down, these simple combinations of carbon and hydrogen are like nature's Lego bricks. They're the fundamental pieces used to build the entire vast world of organic chemistry. From the fuel in our cars, to the fabrics we wear, to the medicines that keep us healthy, it all starts right here. And by mastering the rules of how these little bricks snap together, we unlock the power to design and build the molecules that are going to shape our future.